Hi everyone, this is the first video on the gravitational fields topic for A-level physics. This video looks at gravitational field strength, Newton's law of gravitation and calculations with both of these formulae. We will also introduce satellite motion and explain the significance of centripetal force. If you want to get the free PDF presentation and question sheets for this topic, along with loads of other resources, click on the link in the description. Enjoy the video. Let's consider gravitational fields. Right, various things we need to consider before we start looking at calculations. So, this is a really key point. All masses have a gravitational field around them. So very often we talk about the gravitational field of planets and stars and moons, and that's great, but any mass has a gravitational field, so that's quite important. So if we are talking about a large object, for example, a planet, then we are usually considering a radial field. And all these arrows will point towards the center of the object. So these are to indicate the direction of the force experienced by a mass. So if we have a moon or a satellite or indeed a person stood on the surface of the planet, then they will experience an attractive force towards the center. And this is one of the key features of gravitational fields. It is only attractive. There is no such thing as a repulsive gravitational field. However, if we consider a situation over short distances on a much smaller scale, then we would assume the field to be uniform. So these lines are totally arbitrary and they just remind us that there is an invisible force field there with a particular direction. So we have gravitational field strength. So you should be very familiar with little g. You will have seen this at GCSE and also earlier on in A-level. And very often we consider this as the acceleration due to gravity, which is 9.81 meters per second squared. So within this context of gravitational fields, we call it gravitational field strength. So it's the same value, 9.81, but the units have changed. Now we can show that the units of newtons per kilogram are the same as meters per second squared, and that might be an exam question. But where do these come from? So we know from GCSE that W is equal to mg. So if you make g the subject, then we have weight over mass, and weight is a force, force over mass. So that gives us the definition of gravitational field strength. It's the force per unit mass. So this is quite useful. So if I know that it's 9.81 newtons per kilogram, what that means is if I place a mass of 1 kilogram in the Earth's gravitational field, then the force it will experience at the surface is 9.81 newtons. However, if we go to another planet, for example Jupiter, then as expected, it's got a larger gravitational field because of its larger mass. So the same mass, 1 kilogram, will experience a larger force, in this case, approximately 25 newtons. The next thing we need to consider is Newton's law of gravitation. So this is really important. We need to know the definition and we need to be confident with the formula. And you are given this formula in the formula booklet. So the definition, so we have two masses. So we've got any two masses. Sometimes we add this word point, which means we're not going to worry about the varying density. We'll just assume that all the mass acts at a point. So they attract each other, so this is related to Newton's third law, with a force that is proportional to each of their masses. So the force is equal to m1 multiplied by m2, or proportional to that there on the top, and inversely proportional to the square of the distance between them. So we're divided by r squared. Now we've got to be careful here because r suggests that's radius, and it could be a radius if we have an object on the radius or the surface of a planet. But it's actually the distance between their center of masses, and that's given the symbol r. So just watch out for that. It's not necessarily the radius, it's the distance between the centers. Okay, so we have, this is our general relationship. We have a constant of proportionality, which we are given in the formula booklet. This is big G, not to be confused with little g. There is a relationship between the two, as we will see on the next slide. The negative sign we can effectively ignore. Now we will look at that later on in this topic and where it comes from and how it's related to gravitational potential. But normally we're looking at the magnitude of the force, so we tend not to include that in our calculations. Okay, so you must know the definition and you must be familiar with this formula. So let's look at calculation. This is your standard 2, possibly 3 mark calculation in the exam. What is the gravitational force of attraction between, for example here, the moon and the Earth? So a very typical scenario. So we need the mass of the Earth, we need the mass of the moon, we will be given these in the question. And we can call either one of these M1 or M2, it doesn't matter. And we're given the distance, which we assume is the distance between the centre of masses, which is r. Now it might be a different distance where we have to take into account the radius. So if it's the distance between the surface of the moon and the surface of the Earth, then we might need to consider adding the radius. But normally it will be the distance between the centres. So the first thing we do is substitute into this formula here. So we've got G, big G. We can ignore the minus sign. So just multiply by the masses and divide by the distance squared, and we get this very large number here. So expect to get really massive values of force. So 10 to the power lots, and that's what we would expect. So this would be a typical 2-mark question. So we said there is a relationship between little g and big G, and this is how we derive it. So really important to realize that the weight, which we're very familiar with, mg, and this new expression here, Newton's law of gravitation, the force due to that, they're one and the same thing. So we don't have a weight, and also we have the gravitational force. This is just another way of thinking about it. So if we have a satellite, for example, in orbit, then its weight is the gravitational force of attraction. So mg is equal to big G and 1m2 over r squared. So we can see that one of those masses is going to cancel, and the mass will be the mass of the smaller object. So we could call that a little m, and on the left-hand side, that's just m. So that will cancel, and we will end up with a simplified version. We can include the minus if we want to, but we normally ignore that in our answer. And the remaining mass is m2, which will be the larger mass. So very often this is written as capital M to remind us that's the bigger mass. That's normally the mass of the planet. So again, we can do a calculation here. So calculate a value for little g at the surface of the Earth. So we're given the radius of the Earth, we're given big G, and we're given a value of the mass of the Earth, in this case to 4 sig figs. So we can put the numbers into the formula. So we've got big G, we've got the mass, big M, divided by the radius in this case. So in this case, the distance between the centre of the masses will be the radius. But we need to be careful with that, because if there's a height, we would need to add that on. But in this case, this is at the surface of the Earth, so it's actually the radius. Watch out for kilometres. This is a really common mistake. It's very tempting to just write 6371, but in this case, we've got times 10 to the 6, because we've got kilometres, so all of this is times 10 to the 6, and then squared. 9.83 newtons per kilogram, sounds about right, and that would be the answer in this case. The final thing to consider in this lesson is satellites. Now we will talk about satellites in more detail in future lessons. So the first thing that we would consider is that we assume that the orbit is circular. Now it probably is elliptical, but we assume that this is moving in a circular path. Now we've already looked at circular motion and centripetal force. Now we know that centripetal force is just the name given to the resultant force towards the centre, which is provided by the weight. So if we have the weight mg is providing the centripetal force mv squared over r, then we can get rid of the m, which is the mass of the object. We're not considering the mass of the planet here. And we can get an expression for g, which will be v squared over r. And we talked about centripetal acceleration before, and that shouldn't surprise us that v squared over r is centripetal acceleration. So at a particular height above the Earth's surface, then the value of g, the acceleration due to gravity, is the same as the centripetal acceleration. So let's look at an example. So we've got a satellite, we've got a height of 500 kilometers above the ground. First of all, calculate the value of g. So we've got v squared over r. Well, but we don't know v, so we're going to have to go to our expression from the previous screen, where we know the mass of the Earth and we know the radius. Now we've got to be careful here. So that will be the radius of the orbit, but that's the radius of the Earth plus the height. So this is a really common mistake. So we've got the radius of the Earth is 6,400 times 10 to the 3 kilometers, plus the height, which is 500 kilometers, 510 to the 3. Those two added together is the radius between the center of the Earth and the satellite. And then obviously we square it as well. So we should expect a value slightly lower than 9.81. So even 500 kilometers, obviously this is a very misleading diagram here, that's still a relatively low orbit. So G is just slightly less than it would be at the surface of the Earth. So we can find 8.41. Okay, after that, well, now we've got an expression relating V, R, and G. So we found G, so we can make V the subject. So V is equal to RG square root. So once again, the radius is the total radius. That's the radius of the Earth plus the height, all in meters, multiplied by the value of G that we found. And we get a value in this case of 7,616. Do bear in mind that we would expect to get a very large value of velocity. So satellites are really moving, especially in low or relatively low orbits. Expect hundreds of meters per second. So this is kilometers per second. This is many times the speed of sound. So this is what we would expect. Good, well done. So that is the first lesson of gravitational fields. There are a few more which you can check out on YouTube. You could also have a look at the circular motion videos if you haven't seen those already, because those are a key part of gravitational fields. If you want to get more structured lessons with more worked examples and exam questions and quizzes, then go to payhib.com, grade A physics, and I'll see you in the next video. Bye.